Hi, everybody. Thank you for joining the Canadian Underground Infrastructure Innovation Centre Academy webinar. Today's presentation will be a report card on pipeline soil interaction analysis by Jim Oswell. And my name is Carrie Murray. I'll be the moderator for today's webinar. So organized by the Canadian Underground Infrastructure Innovation Centre, the University of Alberta, and the Benjamin Media, these CUIIC Academy webinars. The Academy offers classes, courses, webinars, and events to help further underground infrastructure educational opportunities across Canada. And the CUIIC Academy webinar series covers a variety of pressing topics, all related to the underground infrastructure sector. Speakers are volunteers that are industry-leading professionals, and they provide this every month. These educational webinars available to the public, and then we'll follow up with a question-answer period. So these are held every third Thursday of the month at 1 o'clock Eastern Standard Time. And the full schedule of events is available on academy.cuiic.ca. And just a couple advertisements here. We have some CUIIC Academy events upcoming in early 2025. So registration is open for all of these. The first one listed is the Pipeline Rehabilitation Academy held in Mississauga, Ontario. So March 5th and 6th. We also have a geotechnical workshop that's being held in Vancouver, British Columbia on March 10th. And then later in the year, we have the Safety Academy held in Edmonton, Alberta, and that's September 16th to 17th. And today we would like to thank our supporting sponsor for the Underground Infrastructure Education webinars, so Westlake Pipe and Fittings. Thank you very much for your sponsorship. And now to make an introduction to our speaker today. So Jim Oswell runs his own firm called Navic Consulting Incorporated. Jim has a wealth of experience, so 40 years in geotechnical engineering. He focuses on permafrost engineering, pipeline engineering, specifically soil pipeline interaction and geohazards. Jim's experience is all around the world in lots of cold places. So Canada, Alaska, Russia, China, Malaysia, South America, and even Antarctica. So with that, Jim, we want to give you a very warm welcome on this December day.
Thank you, Carrie. All right, so So my talk today, I'm speaking to you from Navic's intergalactic headquarters, which happens to be in the basement of my house in Northwest Calgary. And today, what I'd like to talk about is how industry is doing relative to soil pipe interaction. And I've called this a report card. What we're going to talk about is the history, where we came from, where we are today, and what we will, some of the issues that we have going forward. I'm just got some, Allison, if I could ask you, I'm not able to advance my slides. So is that something that you can fix?
Can you hit the next button at the top if you scroll up a little?
Got it. Okay.
Awesome.
All right. Sorry, everybody. Learning curve here. So where we've come from, what are our successes in the present day, and what are our challenges and areas that need improvement going forward. So where have we come from? So soil pipe interaction began over 100 years ago. One of the very first concerted efforts to study soil pipe interaction was at the Iowa State College. A fellow named Marston, a professor there, published a paper called The Theory of Loads on Pipes and Ditches and Tests on Cement and Clay, Drain Tiles and Sewer Pipes. And that was one of the very first publications that started looking at earth loads on any sort of buried pipeline. The work at Iowa State University continued for many decades after. There's a fellow named Marston, and Spangler and Marston wrote a book called Soil Engineering that's very focused on buried pipelines. And that work continued, as I say, for many decades, even into the 50s. And out of that, some of that work came what was called the Iowa Formula, which is a system of analyzing and understanding how soil loads interact with pipelines. And Spangler and Marston were not alone in this. Even Terzaghi in his 1948 publication of Soil Mechanics and Engineering Practice talks about soil loads and the concept of arching. And the Iowa formula, including things like the induced trench method or the imperfect trench method, was developed at Iowa State. And that's got very important implications, for example, for HDD installations. Specifically, what happens is that with the idea of an HDD where you've got a large borehole and a smaller diameter pipe, you've got that annulus filled with softer drilling mud. And as a result, a prism of soil directly above the HDD bore will want to settle downwards into that soft drilling mud. And in doing so, it induces arching. And as a result of that arching process, then the vertical loads that are exerted on the pipe within the HDD bore are less than the total overburden pressure. So the work by Marston and Spangler and even Terzaghi lay the foundations for some of the soil pipe interaction work that we apply today. In the 1950s, the concept of the finite element method was starting to be developed, and particularly at Berkeley, University of California at Berkeley, at Wales in the UK, and at Stuttgart in Germany. They laid the foundations for the finite element methods. And by the 1970s, then they had started to develop shell elements. One of the very first applications, widespread applications of the finite element method in soil pipe interaction was the design of the Trans-Alaska pipeline system that runs from Prudhoe Bay in northern Alaska on the Beaufort Sea all the way down through Alaska to Valdez on the Pacific Ocean at the south side of Alaska. And that pipeline, although everybody sees photographs of the Alaska pipeline as being above ground, only half of it is above ground and the other half is buried. And the buried half has, of course, soil pipe interactions. So that pipeline between 1969 and 1977, when it was finished being constructed, it employed the widespread use of the finite element method. And at that time, then the access to the computers, the mainframe computers, was by dial-up. And anybody who is younger than 60 probably doesn't know what that photograph on the right-hand side is, but that in fact is the modem that is used to connect one computer to another. And I will confess my age because I remember using modems such as that in the 1980s. Out of the work on the Alaska pipeline was a paper by Lucier, Thomas, and Maple in 1979 that talks about soil pipe interaction on the Trans-Alaska pipeline. And it has very relevant information even today on lateral loads and the impact of lateral loading on the pipeline. Out of the need for soil pipe interaction, and particularly in the United States, and the impact of geohazards, specifically seismic events on pipelines, two very important publications were developed. The first one was by the American Society of Civil Engineers in 1984, and a document called Guidelines for Seismic Design for Oil and Gas Pipeline Systems. It's a very good book. It represented the state of the art at the time in terms of soil pipe interaction, and was used extensively to help design pipelines, not only for seismic events, but overall other geohazards and even normal pipeline operation events. In 2005, American Lifeline Alliance, which was a collaboration between ASCE and FEMA in the United States, developed an updated version of the 1984 document and called Guidelines for Design of Buried Pipelines. Frankly, I think the 1984 document is better. I'm not sure if the improvements added to the 2005 documents are as good as what they propose. And in fact, there are some geotechnical errors in the 2005 document. One of the interesting things to look at is when you Google pipeline stress analysis, what do you get in terms of hits for years and things like that? So this table here, this list, and the graph shows that, prior to the 1950s, there were not very many hits when you Googled that. But, between 2011 and 2020, there were 310,000 hits when you Google it, and that's all by age, by year span. And you can see that there's an exponential increase in the number of documents now that are being published. I would argue that not all of them are useful. Some of them are what I would term junk science or junk engineering. So one has to be very careful about when you're looking for a particular topic to have a discerning eye in terms of looking at the actual documents and deciding whether or not it's useful or not. So in terms of a report card, where have we come from? I would give, in terms of a history lesson, I would give it an A. We've done very, very good, very well in the last 50 years or 70 years related to soil pipe interaction. We've made great strides. We've got a very robust system and that has served the pipeline industry very well, both the municipal industry in terms of water pipes and sewer pipes, but also the oil and gas sector in terms of our ability to analyze pipelines. Now, that's not to say that everything's perfect. There are some issues that still need to be addressed, and we'll talk about some of these current issues in the next sort of two sections here. So what are our successes to date? Well, beam and shell models are well developed and calibrated, so our finite element ability is always increasing. Continuum models are advancing, but we still have potential limitations in terms of computer power and our ability to model long sections of pipe. So the traditional way of analyzing soil pipe interaction is by using a beam model with a series of springs. We can analyze pipelines that are many hundreds of kilometers long using this section system. However, if we wanted to do a continuum model and apply things like discrete element modeling or material property methods, which are variations on the finite element system, those require much higher computer efforts. And as a result, we're limited to, say, several hundred meters in terms of pipeline length. We have much better understanding in several areas of soil pipe interaction, including the effect of pipe curvature on the bearing capacity or the downward bearing spring. We have a much better understanding today on earth pressures and their effect on the axial resistance in drain loading. And we are much, much better at incorporating smart PIG inline inspection tools and IMU data into our soil pipe interaction. In addition, we have a better understanding of the backfill temperatures and their effects on the so-called delta T, which is the delta T is the difference in temperature between what the pipeline was installed at and what it's going to operate at. Often a delta T will induce some thermal expansion in the pipeline, and that needs to be accounted for in the design. We've developed areas looking at, for example, for beam elements and the springs, rather than using a traditional bilinear soil resistance representation, we could use a hyperbolic soil representation, and I'll give some examples of that in a moment. So first, looking at our successes, let's talk about the effect of pipe curvature on the bearing resistance. The analogy that we use to calculate the stiffness of the soil underneath the pipeline is based on the traditional bearing capacity equation for a strip footing, so a direct analogy to the foundation engineering concept. But what was discovered was that conical footings that were used in offshore structures, they were failing at a lower bearing resistance than expected. And it was then discovered that that was related to the shape of the footing. And then that was later applied by folks, Young, O'Rourke, and Argargu at a university in New York, which the name escapes me now. But it was published in the Canadian Geotechnical Journal in 2016. And what they discovered was that the pipeline, as it moves downward into the soil, because it's round, it experiences, or the soil experiences, what's called progressive failure. And there is a flow of soil particles around the curved pipeline that results in a lower bearing resistance. This result of a lower bearing resistance, when you're using the standard equations in ALA or PRCI documents, it overestimates the bearing resistance of the pipeline and the soil by about 1/3 to 1/2. So the recommendation now is based on the Canadian Geotechnical Journal article of 2016, is to use the standard equation that are in these documents, such as ALA, but then divide it by about half so that it has a more representation. And that accounts then for the progressive failure. One of the other questions that has been answered and we've gotten a much better handle on and a much better understanding that's allowed us to have better results in terms of our soil resistances is the idea of the concept of earth pressures acting on the pipeline under drained axial resistance. The ALA and some PRCI documents state or imply that we should be applying an at-earth earth pressure. However, laboratory testing on large-scale pipes or near full-scale pipeline has suggested that the earth pressures that are acting on the pipeline are higher than at rest. The equation we show here is the equation for the axial resistance under drained loading, and it is equal to pi d h gamma prime. So that's the diameter multiplied by the depth of burial and the soil. So that gives you essentially a vertical load acting on the pipe. Then 1 plus Ks divided by 2, and that represents the average earth pressure acting around the pipeline, and then multiplied by tan delta, which is a function of the friction angle of the soil. So as I say, in ALA and some PRCI documents, they suggest that Ks value should be calculated using the at-earth pressures. However, the Ks value is a function of in situ conditions, including the stress history of the soil mineralogy, depth, and so that may change. And K naught is traditionally the at-earth earth pressure coefficient is traditionally calculated as 1 minus sine phi, where phi is the friction angle of the soil. However, we know, as I say, from lab testing that that value of Ks is much higher than K naught. So some work by some fellows at Concordia University in Montreal and published in 2018 through a multivariate regression analysis of various data. They calculated a new equation, a empirical equation to calculate the Ks value, and it's shown here. And it's a function of the Young's modulus of the soil, the depth of burial, or the vertical stress, gamma H, the friction angle, and the delta T, which is the thickness of the shear zone that occurs between the pipeline and the soil. So it's relatively very small, often 2 millimeters to 5 millimeters, and the pipe diameter. This is an equation that is purely empirical. It's sort of got no physical basis, but was simply developed on the basis of regression of existing data. If you apply typical values to this equation, for example, using a Young's modulus of somewhere between 60 and 90 MPa and a delta T shown here as 2 millimeters, etc., for a 22-inch diameter pipeline, the Ks value, you can see at the bottom, works out to 1.24. In contrast, the coefficient of active earth pressure is only 0.43. So you could see that by using a Ks value essentially three times the value of K naught, you're going to get a much higher value of axial resistance under drain loading. And that has serious and important implications to your soil pipe interaction. So by using this equation and this research here, we have improved on our ability to more accurately model the behavior of pipelines. And this graph here shows exactly that issue. The black solid line is actual test data from a full-scale test at the University of British Columbia. The short red dashed line that's at the bottom there. That is the behavior, the load, axial load displacement behavior based on ALA. And the dashed dot line at the top is the one that's calculated based on the adapted Ks value. So by using the upgraded, our current knowledge of earth pressures acting on pipelines, we get a much better representation of actual behavior. Now, one of the other areas that we've been able to improve on is the behavior of backfill temperatures and the effect of backfill temperatures on the delta T. And as I said before, delta T is the difference in temperature between what the pipeline is going to operate at and what the pipeline was restrained at. So as an example then, if the pipeline has a lock-in temperature of minus 20, or excuse me, say minus 5, and it's got an operating temperature of plus 20, then the delta T would be 25 degrees. Now, the question is what is the temperature of the pipeline steel at the time of axial restraint? So looking at two American codes, ASME B31.4 and B31.8, they actually give two different definitions. One says the temperature at the time of installation or completion of final tie-in, and the other one says pipeline temperature at the time of installation, tie-in, or burial. The Canadian codes, CSA Z662 from 2015, it refers to the ambient temperature at the time of restraint. And then they changed the language in Z662 in 2019, and it refers to a pipe metal temperature at the time of restraint. So again, we've got these four different codes with four different sort of definitions. And so what's a pipeline, what's a pipeline designer supposed to do? Well, fortunately, we've recently, in the last decade or so, we've done some field research and answered that question. So here's an example of some data what we've done is instrumented both soil and the ground and the trench and the pipeline. We've added thermistors. And the graph on the right-hand side shows the response of the pipeline and the soil temperatures during installation and backfilling. The blue line you see there that goes up and down, that's the air temperature. And then you've got a horizontal line, two horizontal lines at 0 degrees, a dash line and a green line. Both of those represent the ditch bottom or the ditch wall temperatures. So you can see that they are relatively close to zero. And then the red line that you see is the bottom of the ditch. So it's exposed to the air. And finally, you see the black line, which is the average pipe temperature. And in this particular piece of research, we had 3 thermistors connected to the pipeline. And so we were measuring 3 different temperatures, the top and 2 sides. And you can see that during the backfill or prior to the backfilling, the black line is relatively similar to the blue line following the air temperature. But in the 15 or so minutes that it took to backfill the pipeline, you could see immediately that the black line disassociates itself from the blue line and very quickly approaches the same temperature as the green line and the dash line, i.e., what's happening is that as the soil is placed back over the pipeline, as that backfilling takes place, the pipe temperature rapidly assumes the temperature of the surrounding soil and disassociates itself from the air temperature. So that occurs in winter. And so what that tells us then is that even though the air temperature may be as cold as -10 or even colder, the pipe temperature at the time of backfilling very quickly assumes the temperature of the soil. So if one were to use the air temperature as their lock-in temperature, that would be overly conservative. In summertime, we see the opposite effect. What we see here then is the blue line is the air temperature. You see a dashed line that is at about +8 degrees. That's the soil temperature below the bottom of the ditch. The base of the trench is the red line, and the average pipe temperature is the black line. And you can see that prior to the backfilling, the red line and the black line generally follow the behavior of the air temperatures. There's going to be a slight variation because the air temperature is measured above the ground, and the pipe and the ditch temperatures are obviously sort of below in the ditch, and the air is probably a little cooler there in the summertime. But immediately you can see that at the time of backfilling, in this case at 2 p.m. On the particular day, the red line and the black line immediately disassociate themselves from the air and start moving very rapidly towards the same temperature as the bottom of the ditch, that is the surrounding soils. So these 2 examples, both winter and summer, show that the use of air temperature as one of the components within the delta T measurement is inappropriate, and that what we should be using is a soil temperature. And then the question, obviously, then for the pipeline designers is, well, what temperature should I be using in terms of air temperature, etc. And so there is some guidance available on that. So what we've done here is plotted a transect of annual air temperatures from northern Alberta all the way down to Texas. So northern Alberta would be, air temperatures approaching 0 degrees in the Fort McMurray area, for example, and the air temperatures as warm as +17 mean annual air temperatures, down in southern Texas. And with that, we've measured or provided ground temperatures at 1 meter depth in the summertime. That's the top line. with the open circles, and wintertime at 1 meter depth. Those are the square filled in boxes in the bottom line. So for example, if you have a pipeline and you are in the Calgary area and you are constructing it in the summertime, so Calgary has a mean annual air temperature of about 4.3 degrees. You could follow that line up to the summertime and see that our soil temperature is going to be somewhere around plus 14 degrees at 1 meter depth. Conversely, if you're doing this in winter, then you could see in Calgary that our ground temperature at 1 meter depth is going to be around plus 3 or so. And in Fort McMurray, then you would see then that in the wintertime, you would be at somewhere around about plus 1 degree. So what that tells us then is that this gives us new guidance and current guidance for establishing what our delta T ought to be during our design process. In terms of hyperbolic versus bilinear representations, what this does is the hyperbolic curve is of the form P, which is the soil load is equal to the Y divided by A plus BY, where Y is the arbitrary soil displacement and A and B are constants. On the graph on the right-hand side, you can see that the dashed line that goes up and then horizontal is the typical standard bilinear soil behavior that we often use. And the red line is the hyperbolic soil behavior representation. The advantage of a hyperbolic soil representation, there are two main advantages. One is that you can see that it is stiffer at low soil displacements. The curve is more vertical, and then it turns over and becomes horizontal. The other advantage is that it's a continuous function as opposed to the bilinear, where you would get to some yield soil displacement and then the soil displacement would increase, but there would be no increase in load. So it all of a sudden would go flat. So that's clearly not a real representation. It's a simplistic representation. The hyperbolic soil behavior is much more realistic in terms of real soil behavior. And we can find out what those parameters A and B are. Karami, in his PhD thesis at the University of BC in 2006, he did some lateral loads and developed those values for lateral loading piles or pipes. And so here is that representation. There's an actual load test there. You can see the dashed line is the soil bilinear function that they would propose, and then the red line would be the hyperbolic function. And you can see clearly that using a hyperbolic function would be a much better and closer representation of actual soil behavior. And most of the commercial soil pipe interaction programs allow the user to employ a hyperbolic representation. And again, what that has the advantage of is that it's a continuous function over the full displacement of the pipe and soil, plus it's also stiffer at lower displacement values. And that often will result in a more realistic soil pipe interaction behavior. And here in this table, it shows for horizontal and upward loading some values for the A and B parameters. So it's well documented, and that would be something that we could be applying today. So in terms of a report card on our current affairs, I would give us that there is we're at a B+. We have not solved all the problems, but we've come a long way, and we continue to do good research to develop these ideas and improve it. And then that would lead us then to addressing our challenges, that what we need to look at going forward. So some of the areas that I believe that we need to be focusing on moving forward is the behavior of pipelines and HDD installations, specifically the behavior of drilling muds and their medium and long-term behaviors. Pipelines, organic or muskeg interaction, there's a limited research on that. There has been some, but we don't have a clear and robust way to characterize soil muskeg behavior, particularly determining the undrained strength. And finally, the idea, and this is a bit of a soapbox issue for me right now, is the idea of applying risk-based versus consequence-based decision-making to some geohazards. And it's not really a soil pipe interaction, but it's something that I think it's an area that is worth discussing. So looking specifically and firstly at our behavior of pipelines in HDDs, we know that drilling mud has essentially zero undrained strength at the time of installation. That's the whole point of having the drilling mud, to allow the mud to lubricate the bore as we pull the product pipe through, etc. The drilling mud, we also know that it being thixotropic, it will gain strength with time. There are chemical changes that occur in the mud. Water is absorbed into the surrounding soils, and so all of that will change the strength of the drilling mud. But the question for us is, how quickly and how much does that drilling mud gain strength? And it's an area that needs more research. And as an example of this, several years ago, I worked on a pipeline project in Louisiana where they had installed a pipeline via the HDD, and we were doing the stress analysis. And the question became well, what's the strength of the drilling mud? And I had suggested a value to the stress analysis people, and they went ahead and did that, and everything was fine in terms of the stress analysis, showed that the pipeline was going to be safe. But the owner of the pipeline then went out and got an independent assessment, which is certainly their prerogative and often a good idea. And the reviewers came back and said, well, where did you get the strength of the drilling mud from? And after discussions, we conceded that there was very little information on this and that it was an engineering judgment estimate. And as a result of that, then the reviewers said to the owner, well, if the stress analysis people cannot provide a documented strength for that value, then you should use zero. And of course, then when they reran the analysis with zero strength in the drilling mud, they had significant problems with thermal expansion and upheaval buckling that was occurring as the pipeline exited the HDD bore. And as a result, the owner then was looking at having to apply mitigation at the location of the HDD entry and exit points to restrain the pipeline from coming out of the ground due to the thermal expansion that was going to occur in the absence of any drilling mud strength. So there's clearly a need to provide and undertake more research in this area. The one little bit of information that is available is some research from the University of Alberta about 20 years ago. And it shows here 3 pipe diameters, a 100 millimeter pipe, 200 and 300 millimeter diameter pipes. And they were installed in the HDD method, and then they were exposed at different times over a 1-year period, and the drilling mud was measured. It was a relatively rudimentary way of measuring it. For the geotechnical engineers, they simply used what was called a pocket penetrometer. So it's a sort of a ballpark measure of the undrained strength. But clearly, this data did show that the drilling mud did increase with time. The undrained strength did increase with time. I think what you see here is in the separation of the data from the 3 diameter pipelines probably represents the natural variation in the drilling mud strength, and there's nothing to be looked at in terms of an effect of pipe diameter. I think pipe diameter is probably independent, but the differences between the three lines simply represents the natural variation. But here is an area that does need more research. In terms of pipeline muskeg or peat interaction, we know that the most commercial soil pipe interaction programs, they have default values and default soil parameters for sands and gravels and stiff clays and soft clays, but they don't have anything for organics. And often what I have found in my discussions with pipe stress analysis people is that they have often defaulted to using soft clay, thinking that soft clay is a good substitute for organics, and it's not. The peat actually may be stronger than a soft clay, but it's much, much less stiff. And so assuming the properties of a soft clay in the absence of actual data for the peat or the muskeg is a bad idea. And these two graphs sort of illustrate that problem. On the left-hand graph at the bottom, you can see the soil or the deformation behavior for three materials: the sand, which is a nearly vertical line, a soft clay that comes up, and then the muskeg. And what you see from that is that you require a much larger amount of displacement in the muskeg in order to start to gain strength. And that's a result of a number of factors. And on the right-hand side, then you've got what's called the PY curve, that bilinear behavior system that we often use. But you can see then the stiffness of the muskeg is much, much lower. And what we have found from laboratory testing is that the displacement necessary to mobilize maximum strength in the muskeg is often 5 to 10 times that of soft clay. One of the other particular issues that we have with organic materials is estimating what its undrained strength is. And often we will go into the field and we will use what's called a field vein test. It's the most common method for measuring undrained strengths. The problem is that in research in particularly in Europe, in places like the Netherlands and Ireland, they have shown conclusively that the field vein test grossly overestimates the undrained strength of the peat. And that occurs for a number of reasons. But whatever the source is that what we know is that if you measure some undrained strength in peat using the field vein test, it's likely that you've grossly overestimated that actual strength. As an alternative to the field vein test, the current technology is that we should be using a ball penetrometer or a T-bar penetrometer, and they both provide a more accurate estimate of the undrained strength. And then, of course, similar to progressive loading, how does peat respond to a curved pipeline surface? Often we have done previous tests, and as I show here in this previous graph here on the left-hand side, that is a plate load test on sand, soft clay, and muskeg. The reality is that graph may be very different if instead of using a plate, we were using a curved surface. So again, more research is necessary to look at the effects of soil muskeg or soil organic interaction. Now, the final topic that I'd like to talk about, and as I say, it's not necessarily a soil pipe interaction problem directly or specifically, but it's this idea of risk-based versus consequence-based decision-making. We have used risk-based decision-making we embraced it in the 1990s, and it served us very well. And risk-based decision-making assumes that the hazard is well-behaved and will continue to be well-behaved. And so specifically in the case of creeping landslides, we apply this concept. The problem is that some landslides are well-behaved until they're not. This graph here shows some data from ILI, IMU data over a number of years for a pipeline in the United States. And you can see that as they plotted or showed the pipeline displacement from the IMU data over nearly over 10 years, for sure, over a decade. And all of a sudden, in early 1920, the slope failed and ruptured the pipeline. Now, this is certainly not a critique of the geotechnical consultants who were working on this project. It is really a critique of the pipeline operator for failure to grasp the importance of this data, and they fell into perhaps an assumption that the good behavior of this pipeline that was exhibited from about 2007 through 2019 would simply continue. So risk-based decision-making should not be applied to creeping landslides and perhaps some other geohazards. And in doing so, you need to be aware of confirmation bias. That is to say, rejecting data that does not support our preconceived ideas. Also, there is a risk of overconfidence and complacency that are both dangerous, and that what I call tolerization, long-term tolerization. That is, if we can accept, if the owners of and operators of a pipeline can convince themselves that we can tolerate a lower factor of safety for just a few months, then at the end of those few months, then the same people may say, well, that lower factor of safety lasted these last few months. Let's go for another few months before we have to apply some mitigation, and that'll save us money. And the problem with that is that the lower factor of safety becomes the norm rather than the exception. And one must be very careful of that. Otherwise, you will fall into a dangerous trap. Rather than applying risk-based decision-making, I would say for some geological hazards, we should be applying consequence-based decision-making. Now, that would be consequence-based decision-making is consistent with the precautionary principle. And the precautionary principle, as outlined by the United Nations Principle 15 from many decades ago, states where there is a threat of serious or irreversible damage, the lack of full scientific certainty shall not be used as a reason for postponing cost-effective measures to prevent environmental degradation. And so that's the sort of official definition of the precautionary principle. As it applies to us and geological hazards, what I would say is, in the absence of very compelling evidence of ongoing stability, you should assume imminent instability. And one of the things that we can do is apply the principles of high reliability organizations. And many companies are striving to become HROs, and in doing so, they have particular principles that they need to be applying and considering and acting in a prudent and foresighted manner to address problems and issues before they become a major catastrophe is part of that, the principles of an HRO. One of the comments that I've said to senior people at pipeline operators where they're trying to push back on mitigation is the concept that if you think that a mitigation solution for your pipeline geohazard problem is expensive, wait till you have a loss of containment, because the cost of cleanup, the actual physical cost of cleanup on a loss of containment and the cost of reputation and the cost of public goodwill, etc., is going to be much, much higher than the cost of a mitigation that is applied. So that takes us to our current challenges, or addressing our challenges. I think we've done a reasonable job on that. There's things that still need to be pursued and addressed. But overall, I would give the industry a B for our efforts. So overall, where are we in terms of soil pipe interaction analysis? I would give ourselves and the industry a B+ mark. So thank you for your attention. I'm available if there's questions, if you like. And if not, well, thank you and have a pleasant and happy holiday season.
Thank you very much, Jim. We do have some questions for you here, and I'll read them out to you and the audience. So one of them is coming in asking about progressive failure relaxation in the bearing resistance topic. Okay. So the question is, would this progressive failure relaxation of bearing resistance apply to the CUIIC calculation process?
Okay, so is this, as I understand the CUIIC calculation process, I believe, if it's the one I'm thinking of, has to do with surface loading on pipelines. I think that's the only CUIIC document that I'm aware of is surface loads on pipelines. And the answer probably is yes. The issue, and not only does progressive failure we've shown that it occurs in the downward direction, it probably also occurs in the lateral direction. And if anybody's familiar with soil pipe interaction, they would know that the charts that we use for estimating the lateral stiffness and bearing factors in the lateral direction are often based on either two concepts. One would be plate load testing, like plate anchors that are buried and pulled, or alternatively using Troutman and or Rourke work from Cornell University in the United States, and they're on pipelines. And as we know, the lateral resistance based on plate load tests is much higher than it is for the pipeline tests of Troutman and or Rourke. So that's probably also a reflection of the progressive failure problem. But if the questioner could clarify whether or not the CUIIC method is referring to vertical loads and surface loads acting on pipelines, I think the answer is yes, it would. But if there's another CUIIC process that I'm not familiar with, then perhaps they could clarify.
Okay, sure. So we'll watch out for that, but thank you for that. I have another one here, hopefully an easy one for you. Can you share the reference you used for pipeline backfill temperature data?
Oh, the short answer is yes. It's a paper that I and some fellows from the co-author is Jeff Nichols from Stress Engineering, who's now retired, and a couple of fellows from Interpipe. And that is published in, I'm going to say, about 2019 in the ASCE, the American Society of Civil Engineers, Pipeline Systems and Practice Journal. But if somebody wants to send me an email, I am happy to forward them the full reference, etc. So that paper is available in the public domain.
Great, thanks, Jim. I just clicked the slide that has your contact on there.
Okay.
Okay, so I have another one about backfill temperature. So how does soil moisture content impact the backfill temperature?
Not very much, is the short answer. It affects it a little bit because in the backfill, you can imagine a pile of spoil that comes out of the trench and is sitting beside the trench. If it is very dry, it will move towards the air temperature relatively quickly. either in the summer or the winter. If the soil moisture content is very high, particularly in the winter, what that will do is the soil moisture within the pile of trench spoil that's sitting on the ground, it will move towards the air temperature, but because of the high moisture content, it will have a hard time freezing. So, for example, if the air temperature is minus 25 up at Fort McMurray, then the center of that soil spoil pile will remain above freezing for several days to more than a week. And it's a result of the moisture content because it takes a lot of energy for the water to freeze. And so what happens is that the soil gets stuck at the 0 degree isotherm until all that heat, the latent heat of the water, can be released, and then it'll start to freeze. So it's not a big issue, but it generally sort of says is that the higher the water content, then it'll take longer for that soil to freeze and get cold.
Great, thank you. Okay, I have one here about temperature relative to installation temperatures for HDDs and direct pipe crossings. So I'll read it out here, so you have to listen carefully. With respect to delta T and pipe installation temperature, do you foresee any differences in determining the design installation temperature for HDDs and direct pipes crossings?
Okay, so yeah, that's really important because an HDD that will go down, say 30 meters or 10 meters, it's going to be the temperature of the ground down in that HDD bore is going to be much, much warmer than the air temperature is going to be, particularly in winter. The ground temperature will get generally at below about 10 or 15 meters depth or 20 meters depth, the ground starts to warm up all the way to the center of the earth. And so in the upper 10 to 15 meters, you get some seasonal fluctuations in the ground temperatures. It's what's called the trumpet curve. But below about 10 or 15 meters, you reach an equilibrium point where there is very little annual variation in the ground temperature. And as you go deeper, then it starts to get warmer due to the geothermal gradient as we approach the center of the earth. So at 20 or 30 meters down, the ground temperature is going to be warmer than it will be near the surface. So that's important to know because that's going to affect the delta T within that HDD bore. So one wants to be careful if you've got a very long HDD bore that you are accounting for what that temperature is within the bore, particularly at the lower part. For a direct pipe, same thing. I think that's probably true. For horizontal bores that are relatively shallow, I don't think it makes that much difference.
Great, thanks a lot, Jim. I have one more here for you. And it's a question about estimating K0. So are you able to share any insights about obtaining K0 of in situ soils in typical pipeline projects?
So the standard equation for determining K0, which is the earth pressure at rest, is calculated. K0 is equal to 1 minus sine phi. And phi is the friction angle of the soil. Now, strictly speaking, that equation applies to, and I'm going to get into geotech talk here, and I don't know whether the person asking the question is a pipeline engineer or a geotech engineer, but the earth pressure coefficient calculated as 1 minus sine phi is strictly applicable for what's called normally consolidated soils. And one can imagine that a trench backfill, the ditch backfill that is placed around the pipeline, will be normally consolidated, as opposed to this other concept called over-consolidated. And as a result, I think the equation 1 minus sine phi is perfectly applicable to normal backfill that's placed around the pipe. So you can use that equation to calculate your K naught.
Great, thank you. So I think we'll wrap it up there. And yeah, we just want to thank you, Jim, very much for taking the time to present today. And thank you for all those that sent your questions in. And then all of the CUIIC members listed on this table slide, we want to thank you for your membership and sponsoring this webinar, and thank to everyone for attending. And with that, we'll leave it there.
Thank you very much, everybody. You've got my contacts. If you've got other questions, feel free to drop me a line. Take care.